Finally, we're prepared to look at a more realistic cycle on the PV plane. Realistic in the sense that this cycle approximates an actual engine, a practical device. The internal combustion engine, specifically, we'll be talking about the type of engine in an automobile. So it's merely a coincidence that this cycle is named after somebody with the last name Otto, and that it approximates pretty well the thermodynamic cycle happening in the cylinders of an automobile engine. So just a coincidence. It's not spelled like automobile. It's a lot like the pointing vector, right? The pointing vector, which points in the direction of energy flow in an electromagnetic wave. But we're talking about thermodynamics right now. So here is the cycle. Please just ignore these temperatures. These were from a specific problem that we're not looking at. But this problem does appear at the end of your chapter in the 4th edition. This is number 73 of the challenge problems. And I'm going to go through everything presented in the book solution, but also a little bit more detail. So you can observe here that of the 4 processes which make up this closed cycle, 2 of them are isochores, constant volume processes, and 2 of them are adiabats. And both of those are processes which we are prepared to analyze for an ideal gas. We've got formulas for all that. So we should be able to say everything there is to say about this process for an ideal gas. Now, several of the processes have names. So let me just briefly describe what's going on here, and then we'll look at some video, a simulation of what's going on inside the cylinders, and also some actual slow motion video of a cutaway internal combustion engine. QH, this is when the heat is introduced into the gas, the air within the cylinder. So it's a mixture of fuel and air in the cylinders of the engine, and then that fuel-air mixture gets ignited by a spark plug, and in the act of combusting the gasoline with the oxygen, you introduce a large quantity of heat into the gas. And what's a little conceptually challenging about that is normally when we imagine, we've been talking about heat entering the working substance, in this case an ideal gas, as if there's some barrier between the substance and some temperature reservoir. I think I have a graphic here for you. Yeah, so here's how we normally think about it. Here's a cylinder with a gas inside, and the bottom of the cylinder is in contact with this heating coil on an electric stove top. So the temperature reservoir would be the coil, and it's physically separate from the gas. There's a boundary between them. But when you're talking about the cylinder of a gasoline engine, the fuel and the air actually occupy the same volume. And that's a little weird. So this is the way I think about it. When the gasoline is combusted, I think that's a word, it becomes extremely hot. The energy that was held within the chemical bonds of those petroleum molecules, whatever you call them, hydrocarbons, there we go. That chemical energy has now been turned into the kinetic energy of those fast-moving reactants. And I don't know what the reactants would be. I imagine there's some carbon dioxide, carbon monoxide, water vapor perhaps, but those particles are now moving really fast. And I think of that collection of reactants or reactant particles, that is the hot reservoir. That's the high temperature reservoir. And it is in contact with the air within the cylinder because they happen to occupy the same space. So it's a little weird that they overlap, but there's still a concrete high temperature reservoir that you can conceptualize. And that's the hot fuel reactants after the combustion. Okay, now before the spark plug ignites the fuel air mixture, the air is first made to be hot, very hot. So we start over here at 0.1. The pressure is 1 atmosphere because you draw in air from outside the vehicle. There's that intake manifold, and maybe it comes in a little bit warmer because it's already flowed over engine components, but it's basically, the outside air temperature. Let's call it room temperature. And it's rapidly compressed during the so-called compression stroke. That's a widely used name for that part of the process. It's an adiabatic compression because it happens very quickly. Remember, in an automobile, those cylinders are going up and down thousands and thousands of times per second. So it could just take, not per second, that's per minute. So it's a very small unit of duration of time that it takes to compress this gas during one stroke. There's really not time to be exchanging heat through the walls, the metal walls of the cylinder. So it's definitely a good approximation to call that an adiabatic process. And then similarly, the power stroke, this is where you actually extract the useful work from the gas. When that super hot gas that's been heated by the combustion of the fuel, when it's allowed to expand back out to its initial volume, and I'm realizing I can't see the subscripts V min and V max. That might be a problem. This is supposed to say V min, and this is supposed to say V max up here. During the power stroke, again, it happens very quickly. There's no time for heat to be transferred through the walls of the cylinders. So we also model that as an adiabatic process. Now, this is a little more challenging conceptually. So one thing I'd like to point out here is when you're looking at this diagram, you see 4 separate processes. And the engine that we're talking about is often called a 4-stroke engine, but the strokes do not correspond to these individual processes, and I'll explain why. But the only 2 strokes that are actually labeled here are the compression stroke and the power stroke. So the ignition process on the PV diagram does not correspond to a separate stroke. It happens in between strokes. Ignition happens between the compression stroke and the power stroke. That will be much clearer after you look at an animation. And I believe there are actually 2 strokes that happen during this process. So it's like the details have been subtracted out on the PV diagram. You can't see from the PV diagram what the physical piston is actually doing, but you will see it in the simulation. But this is where heat is dumped out of the ideal gas, returning the gas back to its initial state. That's the initial temperature, initial pressure, and initial volume. So I think maybe now would be a good time to look at some simulations.
In the first stroke, the piston travels downward as the intake valve opens and a mixture of air from the atmosphere and a metered amount of gas from the electronic fuel injector enter the cylinder. This is called the intake stroke. On the second stroke, the piston travels upward, compressing the air and fuel to make a highly combustible mixture. This is called the compression stroke. At this point, the spark plug fires, sending the piston downward from the expansion of the air and gas mixture. This is the combustion stroke. The fourth stroke is the exhaust stroke. As the piston travels upward, the exhaust valve opens to release the burned air-fuel mixture. When the piston reaches the top of this stroke, the intake valve opens and the cycle begins all over again.
Okay, I'm going to repeat that, and this time I'll pause and interject with some comments. I've gone too far here.
4 up and down motions are needed to complete the cycle. In the first stroke, the piston travels downward.
Okay, so this intake stroke is actually part of the isochoric process on the right side of the PV diagram. Remember the shorter isochore on the right side? That process includes this so-called intake stroke.
As the intake valve opens and a mixture of air from the atmosphere and a metered amount of gas.
And since air is entering at atmospheric pressure and presumably the temperature of the outside air, that's why we're at that lower right point on the PV diagram. So this is just normal pressure and temperature conditions.
From the electronic fuel injector enter the cylinder. This is called the intake stroke. On the second stroke, the piston travels upward, compressing.
Okay, now we're looking at the adiabatic compression on the bottom as we go from the max volume down to the min volume. This is the first adiabatic process. It's the adiabatic compression, and this is when the temperature is going to shoot up for the first time. Remember, you can increase a gas's temperature in a couple ways. You could put heat into it, which is not what's happening here, or you could squeeze it and do work on it adiabatically. That is what's happening here.
Compressing the air and fuel to make a highly combustible mixture.
Okay, so the temperature is already considerably higher than it was previously, and the pressure. But now it's going to, both of those values will jump up even further, because upon ignition, it's like putting the gas in contact with the high temperature reservoir. The high temperature reservoir being the fuel reactant products. Now, again, you should keep in mind throughout this video, this is all an approximation for what's actually happening. because if they occupy the same space, can you really regard the air particles as separate from the fuel reactants? You know, that seems a little silly, but it's helpful to think about it in those terms.
This is called the compression stroke. At this point, the spark plug fires, sending the piston downward from the...
Okay, boom. There's the introduction of QH. It all happens in one moment. Some of the engines we've looked at, QH gets introduced over, two or more separate processes. But here, it all gets taken in at one point. And you can see that as the fuel is igniting, the piston is already moving down, which means that the volume is already changing. But the ignition probably finishes well before this piston gets back down to its bottom position. And that means you can approximate this as if the ignition happens over such a small time period that the volume hasn't changed at all. In other words, pretend that it happens during an isochoric process, and that's what you saw on the PV diagram. QH got introduced over a constant volume process. So that doesn't really happen here, but it's fairly close, and I have that actual video where you can confirm that. So right now, we've just finished the isochoric introduction of heat, and now we're looking at the adiabatic expansion. This is where the gas is doing output work on its environment, the environment being the piston. This is the whole point of the heat engine.
The expansion of the air and gas mixture. This is the combustion stroke.
Okay, sometimes they call it the power stroke, which I think sounds cooler, but they're calling it combustion stroke. It's that top adiabatic expansion in the PV diagram.
The fourth stroke is the exhaust stroke.
Okay, now, at the end of that adiabatic expansion, you're already down to the top of the isochore on the right side. So remember, that short little isochore on the right side includes two strokes, the exhaust stroke and the intake stroke. So here's the next rather confusing point about this. For all the heat engines we've talked about so far, all the PV cycles, we imagine that we're working with a fixed quantity of ideal gas. The number of moles is fixed and the system is closed. There's no way for gas to get in and out. But here, obviously, the air that's just been involved in that power stroke is about to get exhausted through a valve, and it's not coming back. So we're actually exchanging, used up fuel and air for a new fuel-air mixture. But remember, nitrogen is nitrogen. You can't distinguish one nitrogen molecule for another. And since this whole thing is cyclic and the volume of the cylinder isn't changing, each time we're drawing in the same amount of air and fuel. So what you can do is just pretend that the new fuel and air is the old fuel and air, but it's now at a lower temperature and lower pressure. Because remember, at the intake stroke, well, let me back up. The exhaust stroke, you're dumping out air that's still really hot and still at high pressure. And then you're exchanging it for air that's back at atmospheric pressure and regular temperature. So in a sense, it's like you've cooled off the air that you did have. What you've really done is just replace it with identical fuel and air that's at the initial conditions, but it doesn't make any difference. So that's why the exhaust stroke and the intake stroke can be combined into a single isochoric process. Because think about it, the exhaust stroke, let me back up like 2 seconds. I want to pause it right when it's at the top or the bottom position.
The fourth stroke is the exhaust stroke. As the piston travels up.
Okay, I guess I was already there. Look at the volume within the cylinder. This is what I'm going to call V max. And when the piston gets way up here, there's hardly any space left. That's called V min. So where was I going with this? I was talking about the replacement isochoric. Oh, right. So the exhaust stroke begins here, ends up here. I hope you can see the mouse. And then then the intake stroke ends here. So if you just fast forward or time warp from the beginning of the exhaust stroke to the end of the intake stroke, then your piston just stays right there. And that means the volume didn't change. You get that? So the exhaust stroke and intake stroke, they're just kind of deleted from the time lapse of this whole process and approximated as an isochoric dumping of heat to the outside and a return to initial temperature and initial pressure. Okay, I think now we should look at the cutaway slow motion video. Actually, what I'll do instead, at the risk of being tedious, I'm going to go through this very briefly just one more time, and I will pause and skip past the exhaust and intake so you can more clearly visualize how this four-stroke cycle matches the four-process PV cycle. Okay, so right now you're about to watch the adiabatic compression from the bottom right to the bottom left on the cycle.
On the second stroke, the piston travels upward, compressing the air and fuel to make a highly combustible mixture.
Okay, that was the adiabatic compression. And now, even though you're going to see the piston move a little bit, pretend the piston's not moving. And as you watch all the fuel ignite, that is the isochoric process that goes straight up the PV diagram to higher temperature and higher pressure.
This is called the compression stroke. At this point, the spark plug fires, sending the piston downward.
Okay, it moved a little bit. Just ignore that. Pretend that's isochoric.
From the expansion of the air and gas mixture.
And then what you just watched right after that was the adiabatic, excuse me, adiabatic expansion. That's from left to right on the top of the PV cycle.
This is the combustion stroke.
Okay, now what I'm going to do is pause and take note. Look at the orange color here, indicating that it's still very hot in there and the gas is at high pressure. And then in a moment, when I unpause, you'll see that the gas is no longer hot and it's no longer at high pressure. Okay, I just skipped past the exhaust stroke and the intake stroke, which is equivalent on the PV diagram to going down that isochore on the right side. So see, now the volume is basically what it was before I paused a moment ago, but you can see that the air inside is not drawn with that orange color, indicating that it's no longer at high temperature or pressure, okay? So let's get to the business of analyzing this using the tools that we have available. And I'm sorry to disappoint, but I will not be using a spreadsheet for this particular problem. Okay, let's look at the work done. We have two tasks here. I would like to calculate the total work done by one cylinder. Remember, automobile engines often have 4, 6, or 8 cylinders. We'll be looking at a 4-cylinder engine. And we'd like to know the power output of that engine, because you've heard about the horsepower of an engine. Well, it's kind of cool to use what we've learned in these chapters on thermodynamics to see if we can recover a reasonable number for the output power of this engine purely based on thermodynamic considerations. So there are 4 processes here. Let's calculate the 4 separate works. The adiabatic introduction of heat here, that's ignition. Well, that's easy. It's isochoric, no work is done. You pretend that the cylinder or the piston's not really moving during that time, so there's no work being done. Same thing for this process here. Remember, this process is an abbreviation for the combination of the exhaust stroke and the intake stroke. But instead of considering what's actually happened, which is the replacement of hot gas and reactant products with fresh, cooler air and reactant products, we imagine that we stuck with the same particles and allowed them to shed heat isochorically. Because if you look at the beginning of the exhaust stroke and the end of the intake stroke, the volume is the same at those 2 points anyway. So you can just model it as an isochoric process. Now, the other two are a little bit different, but remember, we talked about this already. There's an explicit formula that's applicable for an ideal gas that allows you to calculate the work done in an adiabatic process. And it's always PV final minus PV initial. So if I look at the bottom adiabat, we've started at that max volume and then compressed the gas to wind up over here. So the final volume is V2. And remember, for the fuel-air mixture, air consists primarily of nitrogen and some oxygen. Those are both diatomic gases, so we're going to go with the value of 1.4 for the ratio of heat capacities. Same formula is applicable along the top here for the top adiabat, but this time the final volume is that max volume. I'm calling it V4 here, but if you note, or if you take a look, there's really only 2 volumes. We're going back and forth between the minimum possible volume occupied the gas. That's when the piston's all the way at the top. And then the maximum volume occupied by the gas. That's when the piston's all the way at the bottom. So we'll be using these in what follows. Let's make a substitution now. The ideal gas law tells us that at any particular state on the PV plane, PV is the same as nRT. That's true for an ideal gas. So let's replace these PVs by NRTs. And what I've done is factored out the NR. And then we'll do the same thing with the work along the top adiabat. At least I will be doing that. Yeah. You see how it works here with the bottom adiabat. What I'd like to do is find the net work done. So I've called it W net. To be consistent with your book, I should have called it W sub S, the work done by the system being the air fuel mixture inside the cylinder. So all we have to do is just add all these up, right? Well, 0 plus 0 is 0, so we're really just adding these two. And now you can see what I've done. I've swapped the PVs for NRTs, and in each case, I've factored out the NR. So let's add these two up to see what the net work done by the system is over one cycle. No, at the very least, we expect it to be a positive quantity, right? We know that because we can see that we're going clockwise around the cycle. That corresponds to positive work. And because we know what an automobile engine does. Of course, it's putting the useful output work into the, the drivetrain of your vehicle. Okay, this is what we're adding up. And we can combine these two terms, right? They have a common denominator. And I get this. And that's fairly straightforward. If we could just somehow determine the temperatures at the 4 vertices of that PV cycle and determine the number of moles we're talking about within one cylinder, we already know what gamma is. We can plug all those numbers in and calculate in joules how much work is done by one cylinder. Beautiful, because that's really not that much calculation. Now, a lot went into this, right? Several chapters of development went into arriving at this formula, so it was not trivial. But now that we're at the final result, it's just a matter of plugging in a few numbers. So I'm going to show you how to use the ideal gas law to estimate how many moles of air are inside a single cylinder. And then some of these numbers we can calculate, others we have to Google because these are things that have been measured. We could just go to the web and ask, what is the temperature of the air fuel mixture inside the cylinder of a petrol engine right after ignition. Now, again, this is going to be the work done by one cylinder over one cycle. But what we can do is multiply that by 4 to get the work done during one cycle for a 4-cylinder engine, and then multiply that by how many cycles are gone through per second. Normally they state it in RPM, but we can convert that into cycles per second, and we'll have the output the output power in SI units for an engine, and we can compare that to actual values for common vehicles. Okay, so let's talk about these various temperatures. T1 is easy. Remember, we imagine that the air is drawn in from the outside. Whether it's a warm day or not, as that air flows over the manifold, I'm assuming it gets a little bit warmer. So a reasonable temperature would be 20 degrees Celsius for T1, and we'll convert that to kelvins and call that 293. And let's see here. In my next slide here, I've got this relation between temperature and volume at 2 different states. And you remember this, right? If you see that gamma -1, we're talking about initial and final states for an adiabatic process. So because this bottom process is being modeled as adiabatic, we can use this equation, which you've seen before, to calculate the temperature here in terms of the temperature here. So this is final, this is initial. I'm going to take this equation and solve it for T2 because that's what I want right now. And notice now, instead of, see how originally I called it volume at state 1, volume at state 2, we only have 2 different volumes here. When the piston's at the top, we call that V min. With the pistons at the bottom, the air is occupying its maximum volume, V max volume. So let's see here, V1. Yeah, that's the V max, hence the substitutions. Now I can solve for T2. Here's what I get. Now let's look at this quantity inside parentheses. The maximum volume compared to the minimum volume. You've seen this as well too. There were the problem, there's that YouTube video I posted called Fire Syringe. And then I did the problem where, you have to compress the air rapidly enough that you can light that match on fire. This is the compression ratio. If you compare the max volume to the min volume, that's commonly called the compression ratio. We will use the letter lowercase r for that. And now we can just abbreviate this as r to the gamma -1. Pretty simple equation. Here's where I plug in 293 for T1. And okay, I'll pause, or I'm going to switch over to a web browser and show you what I found from a Google search about compression ratios. Here it is. Here's what I found from Wikipedia. I consulted Wikipedia for a number of things here. In production gasoline engines from the past 20 years, typical compression ratios fall between 8-to-1 and 12-to-1. So I just picked the average there and went with 10-to-1 as a typical value. My Toyota Corolla, I really don't know what the compression ratio is. I'm sure I could look that up. And now I'm realizing I forgot to show you the actual cutaway slow motion footage of a combustion engine. So let's do that. 16 million views. That's a lot more than my videos. And that's because this channel is pretty awesome. Seriously, check out some of the other videos they've got. But what he's done is cut away a piece of an actual engine, and we have a view into a single cylinder.
Broke our flywheel. That's it for that.
And it reminded me of those clips. Now we're gonna burn a few different types of fuel. The first one is gonna be straight gasoline.
So it could be that this actually was a single cylinder engine, maybe for a lawnmower or some other kind of, you know, like a leaf blower. Okay, so I'm no engine expert, but I believe what we're looking at is a single cylinder. You can see the piston moving up and down inside it. These would be the valves, the intake and exhaust valves. You can see them going up and down at the appropriate time. But what I'd like you to draw your attention to, or I guess I'm drawing your attention to, is the fact that the ignition, the combustion of the gasoline, doesn't actually happen during an isochoric process, but the piston doesn't move down by much before the combustion is basically finished. So the introduction of that, the heat QH can be pretty well modeled as an isochoric process. They're going to switch to slow motion here. It's not obvious when the ignition ends exactly. There's the exhaust stroke. Combustion, it seems to have finished largely before the piston has moved by much. So this PV cycle, you know, I'll put it this way. If you're wondering like I did, like what good is it to approximate this actual thermodynamic process here, even though it is cyclic, what good is it to approximate it with this seemingly arbitrary PV cycle if it's not really exactly the same? Like, how good is this approximation really? And just ask yourself this: can you think of some other PV cycle that would better represent this? And I think that's a very telling question, because you can't. People seem to have agreed that the best way to represent this, at least with simple processes that we actually have formulas for, would be 2 isochores and 2 adiabats. It's not exactly that, but it's closer to that than to any other simple combination that we can think of. And there's another problem in your book about the diesel cycle, and they switch those 2 isochores to 2 isobars, and there's good justification for that. So it's not perfect, but we're going to see that it does lead to a pretty accurate prediction of the output power. Not the efficiency we'll see, but the output power we could do a pretty good job of approximating. Okay, back to my compression ratio of 10. Why isn't the slide advancing here? There we go. Okay, so let's evaluate this equation. Plop in the 293, let R be 10, raise that to the, well, what's gamma minus 1? For a diatomic gas, remember, gamma is 7/5. That's 1.4, subtract the 1, there's your 0.4. So I threw that into the calculator, and I find that the absolute temperature has shot up from, 293 kelvins to 736 kelvins. Now we can go a little further. Since we've got the temperature, we should be able to find the pressure as well. Or can we? Okay, so this is where I had to Google the temperature up here, because really what I'm trying to do here is get the temperature at all 4 vertices. We could talk about the pressure as well, but how am I supposed to get this temperature up here? I could use the ideal gas or proportional reasoning to get T3 if I happened to know what P max is, but I don't actually know what P max is. You know, I knew that this was atmospheric pressure down here because it's drawn from the atmosphere, and I used an adiabatic process to find or I could use it to find P and T here, but I don't know P or T up here. So what I did was Google this, and I'll show you the website that I found. Okay, I'm realizing I made a bit of an error with the website that I consulted. I was looking at this section right here to get information about the type of temperatures you can expect after ignition. So here they're saying at the end of compression, as soon as the fuel burns, it's mixed into the air, and they gave a value of 2,500 Celsius. I also found 2,700 quoted elsewhere on the web, but I didn't realize that I was reading about diesel engines for which a higher compression ratio is used. Do they actually tell us what that ratio is? Maybe you see it, I don't, but I know that this must be a British website. They're saying petrol engines, we call that a gasoline engine, and they actually do use a pressure or compression ratio here of 10:1. So in my analysis, which I'm not going to change because I've already made the spread or the PowerPoint presentation, I'm going to go with the temperature of 2,700 kelvins after ignition, even though they're actually saying here the spark gets the fuel burning, so that's after the spark plug arcs, and then they're at 1,000 degrees Celsius. So I don't really know which number to trust because I found other sites that said something like 2,500 degrees Celsius, even for a gasoline engine, not a diesel engine. So all right, we're somewhere between 1,000 and maybe 2,500. I'm just going to stick with the numbers we've got. At the very least, we can say this. It's 1 or 2,000, not 10,000. So when we look at the output power, if we're order of magnitude correct, we can find that encouraging. So I'm going to proceed with the numbers that the website showed for a diesel engine, even though this is not a diesel engine we're talking about. Honestly, I can't account for the discrepancy there. I'm assuming they're using the same formulas that I'm using. And for a compression ratio of 10:1, beginning at a temperature of 293 kelvins, I don't know why we would only be up at, what was it? Well, they quoted the temperature here, and then they said that here it's only 1,000 degrees Celsius. So let me walk you through my thought process here. Let's also use this relation to find the pressure at point 2, because I'm going to need that as well. So that relation is a little different. Instead of TV to the gamma minus 1, it's PV to the gamma. And P1, of course, is the pressure over here. That's atmospheric pressure. P2 is the pressure here. Let's solve this for P2. This is what I get. Well, this is the compression ratio, which I'm taking to be 10. So take atmospheric pressure times 10 to the gamma. And of course, gamma is 1.4. I plug in numbers. And I find that the pressure here should be 25 atmospheres. Well, let me take a look at the website and see if they give a similar number. Okay, well, they're actually giving a value of 20 atmospheres, even for the gas engine. What did they say for diesel? 35. Okay, my value of 25 is somewhere in between 20 and 35. Okay, now that we know the pressure there, we can use proportional reasoning to find the pressure at the top of that first isochore, right after ignition. So just like we've done in previous videos, if your gas is occupying the same volume, if you're not squeezing your particles into a smaller box, and yet the temperature has gone up from, what was it, 700 something kelvins to 2,700, wouldn't that also imply that the pressure went way up because the particles are still bouncing around in the same size box, but they're moving much faster. So they're going to collide more often into the walls of the container and with greater force. That means greater pressure. So we just use the ratio of the temperatures to find the ratio of the pressures. That's what I've done here. So take the known T3, or the value that I Googled, compared to the absolute temperature at state 2, and multiply that ratio by whatever the pressure was here at state 2. Here's where I'm going to plug in the 25 atmospheres. And I find that the pressure up here, this is the greatest the pressure ever gets during the PV cycle. This is right after ignition, right before the power stroke. The pressure is 92 atmospheres. That's pretty tremendous, right? So you can see, you can kind of feel it, where the power of this engine comes from with those extraordinary pressures inside the cylinders. And you also see why the engine's got to be made out of some pretty strong materials, or it would just be blown apart. You know, you can't make your engine out of tissue paper or aluminum, or at least not, honestly, I have no idea. I'm assuming it's steel. Let's compare with the website here. For gas engines, they're quoting a pressure of 50 atmospheres right after ignition. For the diesel engine, they're telling us the pressure is up at 100. Great. So my value of 92 is somewhere between those two values. So I've got 3 out of 4 temperatures. Let's get the last one now. Since I know the pressure here and the temperature here and the volume here, I can use one of those formulas for adiabats to find the temperature down here. Why do I need the temperature? Remember that formula that I wrote down for the total work done over one cycle, it involved the 4 absolute temperatures. Okay, once again, I'm invoking this relation between temperatures and volumes at the beginning and ending of an adiabatic process. Well, what I'm interested in is T4. So if I solve this equation for T4, I get this. Now, be careful, this is not R, this is the reciprocal of the compression ratio. This is 1/10. Plug in numbers. Gamma minus 1 again is 0.4. And the temperature up here, I was using 2,700 kelvins. Now really, if the temperature was 2,500 degrees Celsius, you add 273, that would be 2,773. But remember, we're just approximating this whole thing anyway, so I think this value is fine. And I find that the temperature at the end of the power stroke, this is right before the exhaust stroke, is still up at a whopping 1,000 kelvins. So that would still be some very hot gas coming out of the cylinders there. And it needs to be dumped out and replaced with new air from outside the car, which is at something like 20 degrees Celsius and atmospheric pressure. Okay, now that we have our 4 temperatures up here in the right-hand corner, let's plug them in. Or can we? What's the one thing we're missing here? We don't yet know the number of moles, but I can use the ideal gas law to find that. So let's look at one point, one particular state on the PV cycle. And if I happen to know the pressure, volume, and temperature for that state, I can solve for the number of moles we're talking about. Now, I tried to guess ahead of time how many moles we're talking about, and I figured it would have to at least be something like 1 mole because gasoline engines are so powerful. They do so much work, propelling your car up a steep hill even, or if you've got passengers, that's quite a bit of weight that you're hauling up the highway. So I was thinking we have to be talking about a sizable quantity of gas, but you'll be surprised it's less than 1 mole. So let's see, what state should I use here? Okay. How did I determine this number? You could look up, what's the diameter of the cylinder and the height of the cylinder, but I chose to use the displacement. So this is a term used by car enthusiasts. You've heard that expression. There's no replacement for displacement. They're talking about the change in volume within the cylinder as the piston goes up and down. Obviously, a larger bore cylinder or an engine with greater diameter cylinders is going to have more power intuitively. So let me pull up a website illustrating this. Wikipedia once again for the wind. Here's a nice little simulation showing the displacement. So that orange rectangle shows you really the delta V. Yeah, it's not actually showing you initial or final volume, it's showing you the difference between the volumes. That's the displacement. Now, since there are 4 cylinders and each cylinder has a circular cross-sectional area, it's not hard to come up with this formula for the displacement. The displacement is the volume displaced by all 4 cylinders together. And by bore, they refer to the diameter of the cylinder. But you can also think about it another way. If you just take Vmax minus Vmin for one cylinder, that is the displacement for a single cylinder. Again, normally when people talk about the displacement of an engine, they're talking about the total displacement of all 4 cylinders. So just take delta V for one cylinder, multiply it by 4, and then this is a value that you can look up. So you may have heard a car having been described as a 1.4 liter engine or 1.2 liters. They're talking about the total displacement. I think my Toyota Corolla is a 1.4 liter engine. That's the displacement of all 4 cylinders together. And remember, you can put 1,000 liters into a cubic meter. So we're talking about 1.4 thousandths of a cubic meter because we'd like to use SI units here. So what I'm going to do is substitute that value here. And by the way, Vmax for a compression ratio of 10, Vmax should be 10 times Vmin. So now I can express this whole thing in terms of just Vmin. And here I've plugged in 1.4 liters. A liter is 1,000th of a cubic meter. Check it out. There's only one variable here, that's Vmin. I can solve for Vmin. Rather than look up the bore of the cylinder and the height, I could just do it this way. So I get that 36 times Vmin's got to equal this quantity. Divide both sides by 36 here, and I wind up with this. And that looks like a very small number, right? But remember, a cubic meter is a huge volume by regular everyday standards of volume. It's much bigger than the volume of your soda glass, or soda can, I should say. Now that I know Vmin, I can just multiply by 10, the compression ratio, to get Vmax, or raise the power of 10 by 1, which I've done here. So Vmax is this quantity. And now we can go back and do what with that? What was I doing with all this? Right. Let's go to a particular state on the PV diagram. Why not start with state 1? That's the easiest one. The pressure is atmospheric. I've just kept 3 digits here, sig figs. The volume is what we just found. This is Vmax. That's when the piston's at the bottom of the cylinder. Ideal gas constant, and of course, the 20 degrees Celsius temperature there converted to kelvins. And here's the number of moles that I find. Now, as I continue here, you may observe that I'm using more sig figs than I really need to. Yeah, I'm just keeping 2 or 3, and at the end, we can round everything, because this whole thing is very approximate. Now that I know the number of moles, I can finally calculate the work done by the gas in one cylinder over one engine cycle. Let's plug all those numbers in. Remember, the temperatures have to be in kelvins. Oh, strangely enough, you wouldn't have to do that here. Do you see how that conversion factor of 273, 273 would have canceled amongst the 4 temperatures? So you could have gotten away with the Celsius temperatures here, but whatever. And there it is, 395 joules. Remember, a food calorie is about 4,000. This is about 400. So this is only 1/10 of a food calorie. It's kind of surprising, right? Like, you explode some gasoline within the cylinder of an automobile engine. This is the engine that can lift your car and you and your family up a hill. And just one of those explosions in one cylinder is 1/10 of a food calorie. Because you can eat that, you can eat more than that in a single mouthful. Even one potato chip probably has more than that. So it's because we've got 4 cylinders and many explosions per second that we actually get the power that we're familiar with. Okay, so multiply that by 4 cylinders per cycle, I find. Now we're talking about, let's call this 1.6 kilojoules. This is a little more significant. And then the next step is easy. Maybe you've observed your dashboard while driving. Very often when you're just coasting, you're doing something like 2,000 to 3,000 RPM. So the cylinders are going up and down that many times every minute. Now, when you need to get away from the cops, maybe you redline it over here. I'm too chicken to redline it. I'm afraid that my car would explode. So I never go anywhere near that. If you're going uphill and towing something, you probably are getting close to that because you need more power. But let's take the number of joules per cycle for all 4 cylinders times a typical value of 3,000 cycles per minute. And then we'll convert that to cycles per second. Check it out, 79 kilowatts. That's a substantial number, because remember, your microwave oven draws something like 1 kilowatt. It's kind of fun to think that your car is putting out a power equivalent to 80 microwave ovens. That sounds kind of scary. I mean, even one microwave oven. You know how if you're standing too close to like your Hot Pocket, and if you accidentally put it in there for too long, or you forgot to open the foil or whatever, and it explodes, that's really startling. So there's quite a bit of power coming out of the magnetron, in that thing. So 80 of those, that's a lot of power. And then lastly, we'll convert it into an imperial unit, which is more familiar. 1 horsepower is the same as this many watts, 106 horsepower. I don't really need 3 digits, right? Let's just call it 100 horsepower. Is that a typical value? Google seems to have all the answers here, and they spit out a value of 120 horsepower for a typical, what is this, like a four-door sedan. I'm actually kind of surprised that the agreement is so good. I think some of that was luck, because we're going to see when we look at the efficiency that while the Otto cycle might be the best approximation you can come up with for the actual cycle within these cylinders, it's still very approximate. So let's proceed now with the calculation of efficiency. Remember, the common sense definition of efficiency is the useful output work that you get compared to what you had to pay for. In this case, you had to pay for the gasoline that went into your car. And gasoline is really cheap. I think it's considerably cheaper than food energy. Like you pay less per calorie for gasoline than you do for food energy. And that's because, again, when you buy food, a whole bunch of people went into getting that to your plate. Somebody had to grow the crops, harvest them, ship them. You know, you got to pay the person to drive the truck across country or whatever. And then the clerks at the grocery store and whoever processed it at a processing plant. A lot of people are involved. But when it comes to fossil fuels, dinosaurs did all the work for us, and the ferns millions of years ago, in the Carboniferous period, big giant ferns everywhere, and peat moss. I don't know, everything died and decayed. I don't know the details, but thanks to them for doing all that for us. We just dig it up out of the ground and burn it. Okay, so we'd like to get as much possible useful output work compared to what we bought in the form of gasoline. Well, the first law of thermodynamics tells us that the output work is whatever's left over after you subtract the exhaust heat from the heat absorbed from the hot reservoir. So again, this notion of exhaust is different from exhaust stroke. They're related, of course, because that is the means by which heat is exhausted. But this is a thermodynamic definition, not a word describing the carbon monoxide that gets sent out the exhaust pipe on your car. Well, we can distribute the QH here. And I haven't talked much about this, but this is a good way to write the efficiency of a heat engine. So all we have to do is evaluate the two heats, and we'll have our expression for efficiency. Okay, well, recall that QH and QC are exchanged along isocaloric processes. Great, that's constant volume. We can calculate the heats using the definition of molar specific heat. So let's look at the QH. My initial and final temperatures are 2 and 3. I've plugged those in here. And for QC, the initial temperature is 4 and the final temperature is 1. But be careful. Remember, QC represents the absolute value of the sum of all those negative Qs. It's a positive number. QC means absolute value. So temperature 4 is actually, that's a higher isotherm. So rather than do final minus initial, which would be T1 minus T4, that would give us a negative number. So we'll switch the order there to make sure that we're talking about a positive quantity. And I did goof that up the first time. It's easy to overlook. So when we evaluate this expression for efficiency, plug in the formulas for your heats. I get this. N and CV cancel. Check that out. The efficiency can be written merely in terms of the temperatures. Now, for the work, we really did need to plug in the various temperatures. But here's something cool happens. We don't actually need the temperatures. We can express the efficiency in terms of just one number, it turns out. So let's go back and invoke this relation, which is applicable to an adiabatic process. Let's look first at the compression stroke relating states 1 and 2. That's this equation here. Remember, for T and V, it's gamma minus 1. And same thing for the top. So what I've done over here on the right in the next slide, I've solved each of these equations for the temperatures in the denominator. See down here? I've rewritten T2 in terms of T1 using this equation. This is what I get. And if you're wondering where I got the R from, again, you're going to have, after you manipulate this, you'll have a Vmax over Vmin. That is the compression ratio. So make sure you see how I got from these formulas for an adiabatic process to these formulas relating the temperatures. So down here, instead of T3, I'll write T4 R to the gamma minus 1. Similarly for T2, and I get this expression, and now you see where this is going. If I factor out R to the gamma minus 1, I'll have a T4 minus T1 on top and bottom. They cancel. And remarkably, the efficiency of this idealized cycle, the Otto cycle, OTTO, depends only on the compression ratio. That's really interesting. There's no mention of which ideal gas you're using, what the temperatures are, how much heat was exchanged along the isocores. None of that seems to matter. It all just cancels out. The only thing that matters is the compression ratio. Now, if you look carefully, we're subtracting a quantity from 1. It would be nice if you could have an efficiency of 1. That would be 100%. So the only way to make this go to 0 would be if the denominator was large. So the bigger your compression ratio, the bigger the denominator, the smaller this quantity is, the less you're subtracting from 100%. And now you see why greater compression ratio means greater efficiency. But how much greater efficiency? So let's graph this. as your solutions manual did. We'll evaluate gamma at 1.4, and we'll graph the output efficiency versus various possible compression ratios. And you can see that there's a rapid increase with increasing compression ratio. But by the time you get up to 10, which is the typical value for passenger vehicles, the marginal increase is pretty meager. So by marginal, I'm talking about the slope here, right? The derivative, the additional increase in eta, that's the efficiency, for an additional increase in compression ratio, rise over run. The slope is leveling off. So is it really worth it to construct an engine with a compression ratio of 30? Because you're not going to have much greater efficiency compared to a compression ratio of 10. And that seems to explain why most manufacturers, they just call it quits at about 12 to 1 compression ratio. Because if you want to compress much beyond that, then you're going to get even more extraordinary pressures and temperatures. And you have to use even stronger materials. And the engine probably wears out even more quickly. So this is some sort of compromise. Now, the disappointment comes in here at the end. Let's use the actual compression ratio of 10 to 1. And I find that the efficiency should be 60%. That would be incredible if your automobile had an engine for which every 1,000 joules of chemical energy liberated from the gasoline resulted in 600 useful joules of output work. That would be awesome. You could drive all over the country and spend half on gas what everybody else does, because I think actual values for efficiency are more like 30%, 20%. In fact, let me Google that. Thank you, Google. I just typed the question in directly. 20%. Ugh. 20 instead of 60? So can we even call this this is a terrible approximation, at least when it comes to the efficiency. So if that part is so bad, then like how did we get such a good value for the output power if this value is so poor? And I don't really have the answer to that question. One thing that comes to mind is the following. When you do ignite the gasoline within the cylinder, maybe not all of that thermal energy actually gets absorbed by the air. Maybe some of it is immediately passed through the walls of the cylinder. They are metal after all, so they conduct heat fairly well. That's the only thing I could come up with. And, so if you could somehow account for which fraction of the liberated chemical energy actually warms the gas, maybe you would find that the efficiency is more like 20%. I don't know. If you have any useful insights, please email me.